I want to introduce the speaker first. So welcome everyone back to this CSP seminar. So today we have Professor Atlas Wang from UT Austin to give us a talk. Professor Wang is leading a large Vita group at UT Austin. And before that, he obtained his PhD in ECE at UIUC with Professor Thomas Huang. And he got his bachelor degree from USTC. Professor Wang actually have a broad research interest spanning from theory to application of all aspects of machine learning. So recently he studies efficient machine learning, learning with sparsity, auto machine learning, learning to optimize, etc. With many applications in computer vision and interdisciplinary science. And his research is supported by a diverse funding grants, and he and his students had received many research awards. If I list them all, I think I will capture a large amount of his talk. So with that, let's welcome Professor Wang to give a talk on sparse neural network from practice to theory. Thanks.
Thank you, Qing. I'm certainly flattered, and thanks for the good words, and thanks for having me here. So without further ado, I see there we're already waiting for minutes, so I suppose I have to stop at 4 sharp. So I'll just start. Today I will talk about one part of my key interest in research, sparse neural network. And actually, every time I talk about sparsity, I feel very risky, because the sparsity is such a keyword that everybody knows a bit about, right? Wherever you come from signal processing, from image processing, from machine learning, from control, everybody has a bit of share about the sparsity. Well, the philosophy of sparsity could come way back to William of Ockham, and also to the artists like Chopin, who told us simplicity is a final beauty. And talking personally myself, when I started research almost more than 10 years ago, this is the first book I read. So sparsity isn't new to the machine learning world as well. And after I graduated, deep learning took over the world. Then sparsity is still not disappearing. For most people studying deep neural networks, the sparsity comes on the name of pruning, and typically was treated as one of the most effective ways to compress deep network and accelerate on hardware. So all good. And that's exactly why every time make me feel nervous talking about sparsity, because it's everywhere and it's still being used. So what new can I tell you about sparsity? That's what I'm going to try today. I could try to tell you some new opportunities of sparsity in the modern deep learning. I do feel interested about sparsity in inverse perfect lines. That's part of my past research too. But today I will only talk about the deep network. And when I talk about the sparse deep network today, I'm primarily referring to neural network whose weights are mostly zero. So it's a sparsely connected computational graph. On this subject, I will first try to convince you should love a sparse neural network beyond just the model compression. Of course, it will solve your multiplications, but that's just a small piece of the puzzle. And theoretically, I will also show you sparsity could give you benefits that you can even probably show some of them. And I will briefly brag about what are the future directions I feel interested to dig more. So without further ado, let's get started. Let's first go to the ad hoc side and look at empirical. For this audience, I guess I don't have to I don't have to prepare about the trend of machine learning world is going big, right? Remember 5 years ago when I first see BERT, say BERT large has more than 340 million parameters. I say, oh, that's huge. And then I see T5, then I see GPT, then I see T5, then I see Clear. And last year we all see GPT, and we all know what we're talking about, a monster, right? More than 10 billion parameters. So with this trend, it's even more surprising to see that going big with neural networks seems to be the solution of all the questions, or at least a large number of the questions. When networks grow bigger, they just become better and more capable at everything. Not necessarily true. Now, this year, people have started to reflect on whether neural network is really better as a compositional generalization or reasoning. But for most simple tasks we used to kill in the past decades, they indeed get monotonic performance gains by just building bigger neural networks. So good. But besides the performance, performance gain, the world also prefer another side, that is efficiency and tiny models. Well, it's no secret to anyone here now that AI models are gaining a big opportunity at the edge. And the edge AI market, the co-designed hardware, the mobile computing, the Internet of Things, all those buzzwords. Government funded them, business wants them, and customers really are attracted by them by their unparalleled intelligence surrounding you, right? The device, the mobile phones, and the things you wear on your vest. So all those things, they cannot afford any big model like GPT-3 or Thinklier. They need to do some very small models. So there is a gap between the market need of smaller models and the performance, the promise where we see at the end of the big models. So how to bridge the gap between the big and small? That was one way sparsity was introduced as a promise. And sparsity has been used as a way to compress the big models to fit into the small resource cost. As I said, typically called as pruning. Let's first start from review something simple. How pruning was done in the old-fashioned word. It's really funny when I say old-fashioned word because I'm basically saying 5 years ago. Okay. All right. So in the old-fashioned 5 years ago, start from random initialized neural network. I will train that until the end and get a pretty mature performant neural network. Starting from there, I can do pruning based on some criteria. For example, the simplest criteria I can do is to just remove element of the small magnitude. More fancy metrics could be found. For example, remove the element with the smallest contribution to the loss or smallest sensitivity or influence function, many of that. Just choose a criterion your favorite and then remove element of the element that are least important on the criteria. You get a pruned network. Well, many weights that are believed to be unimportant under your selected criterion will be removed. So now you get a sparsity which is supposed to be computed and stored more efficiently. However, this pruned network usually come with a compromise of performance. So a typical common practice is to retrain that sparse neural network by fixing the zero and the non-zero map. So if an element is already zero, let's fix it zero, and focusing on tuning the remaining part of non-zero element. Just keep training to restore accuracy. Practically, we will need to do that multiple rounds to get the best performance. So prune a little bit, find out a bit zeros, and keep training the other remaining non-zeros. Repeat the few steps until you have the better, have your satisfactory trade-off between accuracy and efficiency. Okay, all good. Now let me ask you a second question. What if I I revert the order of pruning and training? How if I first prune the network into a sparse computation graph and train that? So let's first reflect why we would need that. Well, pruning is considered as a great way to bridge the big models, the big models cost and the small model and the small device offerings. But think of what price you pay for that for that efficiency get by pruning. I was just hinting you that in order to get a small model by this pruning method, you will need to first train a dense model end to end, and then remove that, and then retrain the model. This retraining cost is usually, again, comparable with this dense end-to-end training. And I further said iteratively, which means that in order to do a successful pruning nowadays, you need to pay the training cost multiple times of a typical dense training. And then you could get a model that can be called efficient at inference. So there's no free lunch in the world. In order to get an efficient model for inference, you need to pay 5 times price, perhaps, as a training time. That's a deal. Well, if you are Google or Facebook, you probably don't worry too much about that. But if you are a poor academic like me, you probably will worry about that. And nowadays, if you look at some of the biggest model in the world, talk about the GPT-3, everybody should worry about that, because even OpenAI claimed they find a training bug in GPT-3's training recipe. They do not have the resource to retrain from scratch. And who dare tell them, okay, I want to do an iterative pruning of GPT-3. Now please retrain me 5 times. I just want to do iterative pruning. That will become absurd. So iterative pruning will incur a cost that are now even too high for everybody. This is the reason why we want to bring sparsity earlier in the training trajectory, even starting from scratch. But what will happen if we directly do that? If we choose some best pruning method to get a pruned network, and then training from scratch with this sparse connectivity. I mean, just remove element, keep them zero, and only focusing train this non-zero element. Long tradition was telling us this is not working. And perhaps it's not too surprising to say to hear that, because training deep neural network is well known to be not that friendly for gradient, right? So gradient training pass back hundreds of layers, and everybody like ReLU neurons and on bad conditioned metrics, everybody is trying to killing the gradient flow when they flow back. So now you give it another kill. You have zeroed down many of the weights during the backpropagation process. So how are you gonna expect the gradient to sustain very well in deep neural network? So no surprise in general, until 2019. I can still recall the time when I came to attend ICLR 2019 and watch the best paper ceremony. I'm not sure how many people here share this experience with me. Well, that was a good old pre-COVID times. All right, so I saw this paper and I was totally amazed by that. It definitely revamped my opinion of seeing the sparsity world. And this paper, the lottery ticket hypothesis, shows that this routine, first pruning and then training, can indeed be possible. That's the main take-home message. And to expand this message a little bit, I copy-pasted the original statement by Jonathan and Michael, both a good friend, and we also collaborate a bit. And I copy-pasted that original word because I cannot say this better than them. Let's read it together. They propose a lottery ticket hypothesis, which states that a randomly initialized dense neural network contains at least one subnetwork that is initialized such that when trained separately, it can match the test accuracy of the original dense network trained from scratch using the same training recipe. That's why it's called lottery. To see that, instead of training this original big fat network, it is possible to have a slimmed down version like this. And when I say slimmed down, it could be 90%, 95%, 97% of the element being zero. You only get two magnitude smaller parameter count in this so-called winning ticket. And when you train this extremely slimmed network from scratch using the same training steps, you get the same performance as the original network. Sounds lucky, right? So that will give you better same performance, shorter same training time, well, two magnitude full parameter is trainable from the beginning, all good. But as long as you really know where is this sparse neural network. So this statement, lottery ticket hypothesis, is what we tend to call as an existence proof in algorithm, right? So it's not even a proof, it's a conjecture. It's an existing conjecture, there exists something. And this hypothesis alone didn't tell you a single bit how to find that existent solution. Fortunately, Jonathan and Michael provide an ad hoc constructive way that can empirically find the solution, so they could claim this hypothesis is empirically true. And now let's look at their ad hoc offer called iterative magnitude pruning. So we will first randomly initialize a dense network, training it like a normal network, okay, just train it. And then just do what we did in classical pruning, remove the unimportant weights. And here, the unimportant weights, importance is just defined by the magnitude. I know that sounds stupid, but the magnitude-based pruning is surprisingly robust in large models. So, well, I will talk about later, but now let's just assume we agree on that. So I prune those small magnitude weights. And after those small magnitude weights has been pruned from this trend model, I will discard the trend weight of the remaining non-zero surviving weight and just keep the sparse topology. I only kill the connectivity, the computational graph. Zero down is zero. They were not connected again. For the others, I don't kill the weight, just keep that topology. And then reset the age values on this topology back to the initialization weight. I don't use their trend weight. They're only auxiliary parameter for me to get this topology. After I get that, I roll back to the same random initialization where I started with. And then repeat doing those two steps. Keep training until you keep training this now sparser topology until convergence, empirical convergence. And then remove a few more small attitude elements. and then get an even sparser topology, and then roll back to the same initialization again for the surviving age, for the surviving weight, and keep doing that until you are happy with the sparsity. Okay, so the most unintuitive part is perhaps we need to reset the remaining weight to their values from exactly. Well, from optimization perspective, it could be considered as a curriculum way to pursue a very hard projection problem, though. But although there are many different ways to interpret why this is necessary. But eventually, when we get this, when we continue multiple round of pruning, getting sparse mask, rolling back to initialization, we will have such a winning ticket, which consists of two parts. Number one, the ultimate sparse mask surviving to the end. And number two, they are original initialization, which should be the same value as the initialization you used in the very beginning dense networks. This is called a winning ticket. I would like to pause a bit here and secretly ask you how you feel about that. I could share with you that when I saw this algorithm first time, I saw this is stupid. Because I was trying to get a sparse network that can be trained from scratch and therefore have end-to-end savings for efficient training. And in order to get that sparse network, I need to again train that network multiple times in this iterative routine to get that lucky sparse network. So why I'm on hell doing that? Okay.
So can I go?
Yeah, please.
Understand. So you are like random initialize, and so when you train like normal, are you training to the end, or are you like
training to the end? That's a classical recipe. Is training to the end. I'll talk about some non-classical recipes soon.
So when you like prune unimportant ways, how do you do this pruning? You just get rid of all the small entries, or
the small entries by magnitude? Yes.
I see. And then when you repeat, you like make the, you're not using the weights already been trained, but you just make the like important ones back to the initial line.
Yeah, apply the sparse mask back to the original initialization and train that from scratch again.
I see.
Yes.
Still okay.
So every time I'm squeeze out a bit more.
I see. Okay.
Yeah.
Got it.
So okay, so thanks for tolerating this stupid algorithm though. I mean, stupid with quota though. Apparently, practically, this algorithm doesn't worth it at all. It's nothing practical except offering an existence proof for lottery tickets. So lottery tickets alone is lottery tickets alone just to show you there does exist a sparse subnetwork. And number two, there is a ridiculously expensive way to find that. That does not lead to the answer to the next question, why this is useful for me. Because obtaining this good sparse mask is ridiculously expensive. I have saw that paper and go back and tell our group, we're gonna open file on that and we're gonna work on that really heavily. And we did in the past few years. So now let me tell you a bit how we turn this into practical. First stuff. Now everybody has gone past the COVID, and we know that there are certain times, well, we don't have a lot of masks around to purchase, right? So if you have a shortage of masks at the house, what do? You reuse a mask. That's the same quote I'm gonna tell you on this page. Well, remind that when lottery tickets become popular, 2019, there is another big thing become popular in the same time. That is the self-supervised pre-training. And when I look at the two sides of papers, I find a lot of similarity between the two. Both lottery tickets and the self-supervised pre-trained weight are very expensive to find. That took a lot of effort. But once they are found, the lottery tickets mask / self-supervised weight, once they are found, they can be reused numerous times by subsequent tasks on different data set and make all subsequent users be cheaper. For example, BERT take who knows how many times to find it, but everybody thank BERT because they can just fine tune it. Lottery tickets is the same. Once you have the good network, can we also leverage its reusability part and amortize its training cost by reusing? So reusing is the first keyword I found. So in the self-supervised pre-training, the key point of amortizing the pre-training cost is to transfer across different tasks. So our first inspiration is, let's follow the setting of pre-training and transfer learning and see lottery tickets is still there. That's what we do. On a pre-trained model like BERT or Sinclair, we pay effort to do lottery tickets iterative magnitude pruning and get a lottery ticket for the pre-trained model. For example, 70% sparse BERT, 90% sparse MoCo. And from this pre-trained network, we have discovered the following take-home message in short sentence. Lottery ticket algorithm can work if it does not start from random initialization, but start from pre-trained initialization. It still works. And what is even better is we can find a good mask on the pre-trained model that the masked sparse pre-trained model can transfer as well as the dense model. This is the transfer learning version lottery ticket hypothesis that we proved the concept. The sparse subnetwork will be the same transferable across different downstream tasks, downstream dataset. For example, for NLP, we could do from glue to squad, tens of tasks. For computer vision, we could do sparse masking on Sinclair and Sinclair MoCo and transfer to classification, detection, and segmentation. So we spent two papers to tell those facts. And recently we find this is still true on multimodality. So that give us the first practicality of lottery ticket hypothesis, because that almost becomes a part of pre-training, right? We make a pre-trained model lighter, so every transfer learning happened on that pre-trained model become much lighter. And that work get a good deal of attention, including a headline from MIT News. So because we are able to reduce up to 90% element from BERT, official BERT model, without damaging almost anything. So that's the first keyword I can offer you. Reusing a mask, and the key and the underlying behind the key, the keyword is pre-training and transfer learning. Second thing, what if I get a mask, but that mask doesn't really fit my face? Well, remember, your mask physically is elastic, and for sparse mask, I'm gonna claim you the same. So we have investigated the next setting. In the first setting, with the transferability was across a different model, was across a different task, and a different data set, but we're still using the same model, right? If you fine-tune BERT, you are forever sticking to the BERT architecture. You cannot suddenly jump to GPT. And in the second one, we're talking about the different level of transferability, which is across architectures. We did another empirical study on lottery ticket structures found between similar network. Similar network here means different members of VGG family, different members of ResNet family. For example, if we have tried to find a lottery ticket first on ResNet 18 and find another lottery ticket on ResNet 150, and observe if there are any relationship between computational graph of the two sparse topology we found on each. And remember, those networks all have very strong regularity in their layer 1 structures, so that enable us some opportunity to compare them on a block-wise level. What we found is really interesting, but not too surprising though. We find that for models coming from the same model family, let's say two different ResNet instances from the ResNet family, their lottery tickets also share a lot of structural similarity as measured by a few graph-based metrics. And that observation motivates us to transform a lottery ticket found on one model to the other model. And for example, if I first find a lottery ticket on ResNet 18, a smaller and shallow model, and I have some way to transfer the lottery tickets into a ResNet 50 by some topology-inspired transformation, that could save me directly doing iterative magnitude pruning on the much bigger ResNet 150, and that gives me efficient lottery fighting as well. That's the second way, transferring between architectures. After the first way, transferring between task and the downstream dataset. So what transformation we're finding? We actually, there's not too much theory behind this paper. We just did a lot of experience in this paper. And one thing we found is, for example, if we have a network, 1, 2, 3, 4 blocks, and each of them we have found a lot of tickets. We find we could we could transform its lottery tickets to a twice the depth network by just doing local replicating of the network of the sparse mask. For example, 1, 2, 3, 4. This is a 4-layer for simplicity. How to make it 8-layer? Several successful patterns we found include 1, 2, 3, 4, 1, 2, 3, 4, 1, 1, 2, 2, 3, 3, 4, 4, 1, 1, 1, 2, 2, 2, and 3, 4. There are several successful patterns compare. And I remember the best pattern is 1 in the middle, 1, 1, 2, 2, 3, 3, 4, and 4. Although we don't have a theoretical backup rigorously in this paper, we did raise a few hypotheses why that happens. If you could check our paper, we provide an explanation why this sparsity could self-replicate locally by understanding ResNet and its symbols as an unrolled estimation or had a dead or dynamic system, which was first proposed by Thomas Boggio's highway network view. So, and by interpreting the ResNet as a discretized ODE, we could consider interpolating sparse mask as a discretization with more steps. This is just a conjecture, but nothing rigorous. But on the other hand, empirically, we indeed find this transformation to work quite universally across a different structure, not just ResNet family, but also VGG family. So the transformed transformed lottery tickets, here are the ETTs, elastic transformed tickets, there is still slightly inferior to the best IMP lottery tickets, but almost outperform all other pruning methods directly working on the target architecture, while saving a lot because I only work on small architectures. So that was the second. Was the second story told to tries to tell. Transfer from small architectures, make your life easier. So far I have been talking a lot about transfer, right? So that all based on grounding something existent. But how about training from scratch? The real deal, the real big deal. For this audience, expert audience, guess I don't have to brag about how expensive machines are.
Can I ask a question?
Oh, please.
So when you do this transfer of the mask, is there any intuition why this transferring the mask? Because the data, I mean, the pre-trained data and the downstream data could be very different. Like distribution could be very different than why this kind of transfer of the mask works here, or any intuition?
I tend to think in this way, I tend to think the pruning itself as a special neural architecture search. So you are actually pruning the architecture towards a sparsified version, a less parameterized version that can work on this family of data. So when you do downstream transfer, you expect the same architecture to work again. You will not be surprised if a network searched for ImageNet classification can also work on some other similar data sets classification or detection, right? It's actually what many NAS papers would do in transfer of tasks. And I consider here the transfer learning would also be transferable across different tasks, but with some similarity. For example, I'm not claiming this to be infinite. We did have another paper show that if I find a lottery tickets on image restoration, it cannot transfer to image classification. So there is a limit. So that's a full story.
I see. So when you like transfer the mask from like say ResNet 18 to 50, the dimensionality of each layer could be different. Well, so let's say you just preserve the topology instead of just the. I mean.
Well, actually, the dimension is 5. If from 18 to 50, there you need something, but because 32, there will be a resolution change. But if, for example, for 32 to 56, or any transformation like 12 to 18, like beyond 30, that transformation will not encounter any dimensionality issue. Only if you cross the bar of 30, there is a resolution change where you have to use our interpolation.
I see. Thanks.
All right, thank you. So next question I'm going to talk about is training from scratch, how sparsity can help. What if I have nowhere to borrow, nowhere to transfer? So while lottery tickets has been stating we need to train multiple times, there is a surprising finding that lead us to more efficiently use sparsity for training from scratch. Surprisingly, we have observed that when we use pruning, here I need to clarify. Here I mean structural pruning, so on channel level. When I use channel pruning during each epoch of the training steps. For example, I train ImageNet train ImageNet with 90 epochs, and after each epoch, I can do a channel pruning. And then after do the channel pruning, I could look at the surviving topology on the channel level and compare two consecutive epochs topology change. So we have done that for a range of models, and we have found a very interesting observation that the topology of intermediate channel pruning actually stay very stable after the first early epochs. In general, in the first, the topology, here the topology means the strong response channels in the model at the current point. The topology, which indicates the set of important channels, will first be very chaotic and change very quickly from epoch to epoch. So that happens especially heavily in the first 5 epochs. And then after it passes 15 to 20 epochs, for example, in ImageNet case, we find the important channel designation are basically fixed. So intuitively, I'm trying to describe the ImageNet or the network training dynamic to be work like this. So in the first few epochs, the first 15% to 20% of epochs, the network is first to decide, okay, I got this many of channels in my team. I will first divide the job. Okay, channel 1, you should be responsible for this. Channel 2, you should do this. Channel 3, you are useless. I will first do a workload allocation and decide who will work on who. And that is a substantial change period. Which channel is important, which channel is unimportant in the first stage of training. And then after this job designation is done, important channel and unimportant channel have both been decided in this round of teamwork of training. And the stronger model, the important channels will now just start to do their work, and unimportant channel are free to be removed. They will not be called back into this teamwork. The interesting evidence supporting that is we find that when the channel map, importance map, stop changing in training, in fact, the accuracy is still trivial. ImageNet, that's around 60% something when the channel, important channel got fixed. So that observation tells us there is important sparsity pattern emerging at the early stage of training that you can extract now rather than later and wait until the end of the training. So pruning can happen early. That's the main observation. And that leads to our algorithm called early bird lottery tickets. So the main idea is to leverage this early emerging sparse topology and train early stop the training, get a sparse topology, and continue train only sparse network. This is a simple idea, but it works on a large range of networks from convolution, BERT, and VIT. We have 2 papers describing their concrete experiments. So that's training. That's a second. So that's how sparsity could help training from scratch as well, besides the transfer learning setting. And now I'm gonna switch the gear and tell about the third thing. Tell a third story for you. So far, I have been telling you there exist some lottery tickets, right? Good lottery tickets classical, lottery tickets transferred, lottery tickets early emerging. But I'm keeping hinting you that there exists someone particularly lucky, and it's worthy to pay some price to draw that lottery tickets. I'm gonna tell you another story. No, you probably don't need to pay the tax of finding the lottery tickets. Let me start by asking, if I ask you to write a Python code, write a Python code to do proof on the network, what you can do with 1 line of Python code? Not even a 4 iteration. I guess the most simplest thing you could do is random pruning, right? Just randomly do a Bernoulli sampling of all the elements regardless of what, and then put them to 0. That's the simplest thing you could imagine. Without any surprise, random pruning has been considered as the poorest the paper of the baseline of all the paper, and everybody will list the random pruning nicely on the first row of their comparison table and say we beat them by 20%. So all those good fancy pruning method has treated random pruning as trash. Is it true? It's probably true for post-training pruning. But next, I'm going to tell you, for training from scratch, random pruning is probably very strong. I will now present you a cooking recipe of random pruning so that you could start from a random sparse mask, which is almost free, instead of using an expensive lottery ticket mask, even a good priced early bird tickets. I don't need to use that. Let's use the free random pruning to get a mask that can be as good. And now let me tell you what's the key secret sauce. So sorry, again, we did a lot of experiments in this paper. You can see from the title how I was happy with that. So the title we call it the unreasonable effectiveness of random pruning. And we find there are two things matter. We tried a lot of confounding factors. Only two things matter, statistically matter. Number one, the bigger the better. If you are pruning me on the net, then yes, please go to optimal brain damage. If you are pruning me on ResNet, go lottery tickets. If you are pruning me something way bigger than ResNet or DenseNet, we find that when the network grows sufficiently wider and deeper, all the pruning become equal. That doesn't make much difference. So when go large models, it's actually a blessing. Probably you don't necessarily need expensive pruning. That's story one. Secret sauce one. Secret sauce two. So this is the first, the problem setting. You need large models for my claim to be true. Random pruning can work as well. Number two, there is also a reason, there is also a key factor we find for pruning to work well. That is layer-wise sparsity ratio. So it seems sparsity allocation per layer is a key resource allocation question, decide the gradient flow. In fact, a few advanced pruning methods, such as the snip, grasp, and SynFlow, all care about how to allocate the sparsity ratios. We have proven, so we have shown in this paper, there are a classical or random graph generator could be used to automatically assign sparsity per layer in a totally data-free manner. No training is needed, neither. So it's a distribution come from the Edelserian kernel, and the effect is basically if this layer is wider, then I will give it a higher sparsity. If it's a bottleneck layer, I will give it a low sparsity. High sparsity means more elements being zero. So the concrete mask could be found in our paper. With just two secret recipes, the sources, the take-home message I'm always proud to share with people is we are able to make a random pruning work on ImageNet level. A randomly pruned subnetwork of wide ResNet 50 can be trained from sparsely from end to end, and the resultant accuracy is as good as the dense wide ResNet 50 on ImageNet. Here I need to clarify a common confusion. Well, people commonly ask me that so first, one successful foundation of this work is model need to be sufficiently large. I can tell you, if I use ResNet, common ResNet, normal width, random pruning is still not as good. But if I use a wide ResNet and I make it 4 times wider than typical ResNet, random pruning start to catch up. So people come to criticize me that so it sounds like you are really slashing yourself because you first make this network bigger and then add sparsity to make it smaller. Why don't I start from a smaller model from scratch? Good question, but I invite you to look at the statement again. I'm not saying that a sparse subnetwork of wide ResNet can match a shallower network or smaller network of its same parameter count. This is not my statement. My statement is a wider network, its random sparse subnetwork can match the performance of this super big super big dense network itself. So you are getting this enlarged performance by paying a sparse price. That's what I'm telling here. If I can only match the performance of a comparably parameter count smaller dense network, I will not be surprised. And in our paper, we show we actually outperform that one, smaller dense network. So we also show that in our paper, once the network grow from shallow to deeper, from narrow to wide, we see an empirical monotonical trend, the gap between random sparse mask and the lottery ticket mask to close. So this is actually a blessing because when the model gets larger, we don't have the luxury to retrain multiple times and get a really expensive sparse mask if random sparsity can work. That helps us. Plus, we also tested in this paper, it has many other good properties besides just accuracy, as long as it can work. So I'll stop here about this random sparsity, but I will come back after 2 slides. So before my last page, I'll tell you on the empirical side is I'm trying to convince you that sparsity has more things I don't have time to cover. So first, we have papers show that sparse network tend to be more data efficient. So it's an extremely simple but powerful tool for few shot learning. So we have validated both image generation and image recognition that sparsity lead to perhaps state-of-the-art few shot performance as long as sparsity is used right. And sparse models if transmitting sparse models, we can save bandwidth. So clearly sparsity can have a role in federated learning for communication efficiency. We also show that. We recently also started to do some neuroscience experiment with our colleagues in bio department and show some of our sparse patterns found by RMP can actually be validated on monkeys' brain in the computer interface pattern. And one side knowledge I learned from this experiment is a monkey is way more expensive than a PhD student. And also we find the sparse neural network appear to be more robust in many ways. So empirically, we have validated that for adversary attack, backdoor attack, outlier detection, and also we can ensemble sparse network to make it work even better. We also have a relatively theoretical paper on ICML this year show that certifiable robustness will also provably improve with sparsity being introduced. With that, that's my first part of empirical. So Qin, should I continue or wait for questions? I see I'm a bit short of time.
Is there any questions for Atlas from audience?
This is all my empirical stuff, and then I will switch gear to talk about the theoretical stuff.
Oh, maybe you can proceed.
Okay.
For ask question at the end.
Okay, sure. So the second part is I want to understand some of the most intriguing behavior discovered by myself in sparse neural network. So some of you probably know that in Silicon Valley, there's a famous saying that you should eat your own dog food. And for me, experiment is my dog food. And I have to eat that, and I have to prove something to make sure I didn't do the experiments wrong. So the first thing, so I started from something that surprised me perhaps the most, maybe you the most as well. Sparse network can be optimized. Randomly sparse network could be optimized as well as dense network. So we try to justify this is perhaps true, and we have a paper justifying so using the tool of neural tangent kernel. I know many people here are expert of neural tangent kernel. Basically, when you run a stochastic gradient descent on overparameter neural network, it can rapidly drive the training error to 0, and the weight of the network have a small change after training. It's called a lazy training regime. And so because the change is really small, you could do a tail expansion of the training dynamic on the weight change, and that provides you a linear dynamics that is easier to analysis and easier to analyze and predict. So we utilize this tool to, so this linear dynamics is governed by a kernel called the neural tangent kernel, and this kernel is decided by the initial stages, Jacobi matrix. So we want to use this simplified proof regime. It's a larger simplification of what actually happens in training, but also, because we are doing random pruning, the random pruning, it gives us some convenience improving this, convenience in pruning with NDK, which I will show you next. So the target problem we try to answer is, how good a random pruned subnetwork could actually be compared to the original dense network under the neural tangent kernel assumption. And this is backed up by our experimental result. Now we need to solve the theory. I probably don't have time to go through the proof techniques, but I can show you some main theory result we get. So first, the asymptotic case. Here, asymptotic means the network width could be infinitely large. And in this case, the conclusion is actually trivial. If the network is infinitely big, then a sparse subset of infinite big is still infinite big. And also this is a linear regime, and sparse masking is just multiply weight with another linear mask. So really nothing too this proof is actually very easy. So so this is the first theorem. Basically tells us if we prune random pruning after initialization, the N network width approaches infinity, the empirical NTK will approach the original NTK and only up to some only up to some multiplicative scaling factor. And this scaling factor alpha power L is the network depth and alpha is the sparsity ratio per layer. We assume uniform sparsity per layer for simplicity. So this basically shows that you want to have a convergence rate impact other than constant value. And of course, a sparser network will make the optimization slower, but that's it, constant level. And if you further care about the generalization, you know that in NTK generalization, people know that it's about the test kernel over the training kernel. So this multiplicative factor can even be canceled and shows that the sparse network can generalize well in this infinite regime. So really, this is easy, nothing too much to say. And if you're interested, you can look at our paper. But now I want to talk about the second more interesting result in the same paper, non-asymptotic case. So the result, so the question we want to ask in the non-asymptotic, say the network is of a finite practical width is, once we have pruning, fixed pruning probability P, let's say our sparsity level is fixed per layer, how wide is called wide? How wide this pruned neural network has to be in order to say this pruned network can approach the dense network in the neural tangent kernel regime? This is what we target answer here. Empirically, we already have the answer. On ImageNet, make it 4 times wider than ResNet, then you can observe that. Now, theoretically, what it is. So our main proof regime follows a classical paper by Sajiv Arora and Simon Du in 2019. And they analyze the dense network, and you're using a key trick called a Gaussian fresh copy. So I don't have time for the details. So one thing I insist my student write in the abstract is please do add this sentence in abstract. It's misleading to think this non-asymptotic proof is trivial on top of Sajiv and Simon's work. The key barrier here in the proof is a Gaussian copy trick. Key issue here is they assume Gaussian weight at the initialization. And if you have a Gaussian random vector with 2 factor vectors, W and XY, so W is Gaussian. If XY inner product is 0, then W transpose X and W transpose Y is independent. This is the Gaussian this is the Gaussian independence. And this property is used to improve their backpropagation. But remember, this property is not holding for general variable W beyond the Gaussian. And for proof, this will create a critical bottleneck. So we are not able to go through this Gaussian copy trick in their proof. So we create another trick by separating the mask and the weight and consider the mask to be part of the activation rather than the weight. So we can then apply the Gaussian copy trick to the weight, and then we analyze the sparse realization of the activation. The details can be checked in our appendix. I need to fly over due to lack of time, and jump to the conclusion. So there are 2 things I want to see in the conclusion. Here we have characterized the minimum depth each layer could need to satisfy in order to be called wide enough. There are 2 key components compared to Simon's result. So I'll play back what Simon's bound look like. It's here. L is the number of neural network layers, epsilon arrow, and the epsilon arrow. And this is for the minimum depth of all the layers. The minimum depth should be larger than this. So now take a look at this. And going back to our result here, you will see some friends. Okay, so there's L power over the L slash over epsilon slash or something. But you also see some new faces here. Number 1, there is a 1 over alpha square. So this alpha is a sparsity. So it's no wonder that if you have a very high sparsity, this alpha will be smaller, which means that each layer need to be wider. So that shows that if you want to get high sparsity, you indeed need to exchange for wider networks. The second part is a polynomial term on the log on the right. So this is non-existent in Sajiva and Simo's result, and it describes an interesting disentangled relationship between different layers width. Here, dh plus 1 di means, so di means the width of different of the ith layer, and I from 1 to L. So a direct consequence of this bond is we show that it's impossible to just increase one layer's depth without affecting the others. If you want this network to be wide enough, you have to make all the layers grow its weights proportionally instead of just increasing some of them. Even there is one bottleneck, it will be a bottleneck for this sparse network's training dynamics. This seems to be new over the dense network. One thing I have to remark here is I don't comment this bond to be tight, because Simon and Sajiva's paper, which we build many of our ideas on, also do not claim tightness yet either. But we offered some empirical experiment in our paper to show the two key points I just described to hold: the relationship of minimum depth and sparsity, and also the proportionally growing relationship of width when sparsity is present. So these are just some results. I'm gonna fly over them. Some other theoretical result we looked at in sparsity is number one, why there exists a universal sparse mask. We have a paper in this year's ICML, and basically use a statistical tool called Ising model or renormalization group theory to show that a sparse network could be modeled as a critical part, as a multi-particle system where each particle has its critical temperature for phase transition. This is thanks to the first author, which is a theoretical physicist, a friend, and he contributed that unique angle. And we use that theoretical physics tool to prove there should exist such universal mask. And this universal mask is only dependent on the architectural topology, but independent of the actual weight, which shows that you could get this same architectural work independent of the weight and therefore data. So different training distribution will converge to the same fixed point. That's the key finding of this paper. And some other things we look at is how sparsity could help fix overfitting and help improve the data efficiency. Those are some pending works that some just submitted. I'm happy to discuss offline for more. So for the last few minutes I want to talk about a few future things that we're actively working on, which are the new sparsity I personally have enthusiastic about. So the first thing I'm happy about is we are recently using sparsity to train, tune, and evaluate new big models. So we have most of the works I described today is about element-wise sparsity, but we have extended this into sparse matrix factorization and introduced the high-order sparsity. That is currently we are representing a dense matrix with its sparse approximation, right? So D1, that's projected to S1 using some projection. In our newest algorithm, we have decomposed a dense matrix into a product of multiple sparse matrices, and sparse matrix factorization can be way more representative than the current ambient sparsity. We show that while current sparse model cannot work, current ambient sparsity, element-wise sparsity cannot work when it comes to beyond the GPT level, this factorized sparsity can better preserve the expressiveness, and we can make it work for GPT-2, and most recently, we make it work for AlphaFold 2. And for both models, we are able to generate some new exciting applications. So for example, for AlphaFold, when we use our sparse tuning, we could do very few short tuning of the AlphaFold prediction on some very targeted proteins. For example, COVID vaccine, we are currently working with our biochemist colleagues using our sparsely tuned AlphaFold. Another thing which yeah.
So are you saying is that instead of just tuning doing this sparse mask on the weights, you are say the weights have some low rank factorization, you are
not low rank, I use the sparse matrix factorization, so multiplication of multiple sparse matrix.
I see.
Yeah, and low rank is another good mention, by the way. So another thing I'm pretty excited about, dynamic sparsity. So far, no matter lottery tickets, early bird tickets, lottery or random sparse mask, I'm talking about sticking to the same mask from end to end. But there are also algorithms who allow you to dynamically change the sparse mask during training based on the training dynamics. And in year 2022, people perhaps most familiar with this one, sparse mixture of expert, right? So every instance could get its own sparse routine. It's no longer element-wise sparsity, but also modularized sparsity. And Google was selling this very hard. So we also collaborate with Google's mixture of expert team, and we have recently caused a few things. We have also used sparsity to scale up models. One wild thing we recently done is we find we could build sparsity into the design of the convolutional kernel itself, and train a model with a convolutional kernel size as large as 54 by 51. But with this big kernel, most elements are being 0. We show that training this big sparse kernel is trainable from scratch, and this kernel generalizes better than small kernel stack, so kind of challenging the convolution network's design philosophy. And the last thing we just delivered latestly is a benchmark to evaluating current sparse algorithm. The web page is not public yet, so the paper is currently under review somewhere submitted last month. But we are able to show that if the network scale up much bigger and the data scale much more complicated, we can create a new training technique. We can create a new data set and a new model where almost no existing pruning method or sparse neural network can work. It's extremely fragile to sparsity, including the lottery tickets hypothesis. So I don't have time for detail, but we have created 4 different new tasks, 12 different data sets curated from our research practice, and bring you a big message. No sparsity works on this benchmark. I'm pretty happy with that because that means I have more work to do next year. And with that, I'm ready to conclude my talk and pay the attribute credit to the right person. So those two, Xiaohan, Tianlong, and Shiwei are people who do the experiment. This guy, Hongru, did the theory work with me. And I should not forget to mention that this guy, Tianlong, is currently looking for a job. He's, to be very honest, he's way better than myself. And I hope he will be able to land somewhere well, and I hope some of you will enjoy his work. That's all my talk today. Thank you so much.
Thanks, Atlas, for the great talk. Any questions from the audience? So I have a question. So we were doing this large kernel, sparse large kernel. So what's the intuition that you want to use this large sparse kernel here?
Oh, the intuition is actually to see the big contrast between convolution and self-attention. Convolution network has seen the design trend of stacking deep with a small convolution since VGG. But recently they have been taken over by vision transformer who claim their performance because of the larger receptive field, right? The global receptive field. Every pixel can see everybody else in the global image. So we just feel there is a big gap in between the two philosophies. So we are trying to see if we first try to see if we could expand the convolution larger by some clever parallel computing implementation, and then realize that if you use a very big convolution, then first the memory will explode, and second, it leads to training over smoothing features because the convolution try to summarize the features shared in shift invariant way across different regions of the image, right? So if you indeed just brute force train a big convolution, the big convolutional kernel, the kernel is visualized to be something like an average filter. So it does not, this big convolution filter will over smooth things, lose too much details, and do not extract the sparse features we want. So in order to push out that sparse edge, sparse corner, those features we want in high frequency, we inject sparsity. And sparsity also kills 2 birds with 1 stone. It enforces discriminating features to be extracted, and it also saves the memory burden. And performance-wise, it's better than Swing V2 and everybody else we know when we publish this paper.
So you are saying that this kernel could have some like more orthogonality? I mean, it's more like an orthogonal kernel.
Well, not really. So conceptually, I'm just talking about. Yeah, conceptually, I'm just talking about a big convolutional kernel, which is 2,500-ish element, but perhaps more than 2,000 elements being 0. And which element being 0 are selected by dynamic sparse training. We have the way to automatically decide them during the training based on their usage.
I see. Thanks.
Yeah. eventually every kernel is highly sparse. Okay, yeah, please.
There's a question from Matt. Can you unmute yourself and ask a question?
Yeah, so like obviously when you're making sparse models, there are fewer operations to perform when you're sort of doing evaluation or training, but how does GPU optimization and things like that factor in? Because if I'm not mistaken, a lot of these hardware systems are meant for dense multiplications. So like how do you scale that?
Okay, so great. This is almost a question I got on my every paper on sparsity publishing last 3 years. So we already have a template to answer that. I will repeat that template for you. So number one, there are already some computation infrastructures that can support unstructured sparsity at high sparsity levels. For example, there is a paper called Fast Sparse ConvNet published by Google in CVPR 2020 that shows that they could use quadruped sensors on mobile phone to accelerate unstructured sparsity between 70% and 90%. So unstructured sparsity is not absolutely unaccelerable, but high unstructured sparsity could still turn into efficiency. So that's my first point. Second point, we are able to, what I keep emphasizing during this work is sparsity is not just benefiting you from the efficiency perspective. Even not talking about efficiency, we have many other benefits such as memory, such as robustness, the things that didn't have time to cover, and eventually performance, like those big convolution things. So that the performance gains are independent of whether we save efficiency or not. And number three things is there are actually several recent progresses make lottery tickets and unstructured sparsity pretty practical, more practical than ever. I'll mention two things. Number one, there is recently a technique that can remap on the compiler level to remap the unstructured sparse element into N over M fine-grained sparsity, which is now supported by commercial GPUs of NVIDIA. And that technique was developed by us and published in ICML this year. Using that technique, you just need to write some Warper code. You don't have to rewrite any CUDA. It's just doing some remapping and help the compiler process in the most streamed way. So there exists some technique that leverages some compilers' clever tricks to make acceleration possible for unstructured sparsity. That's a take-home message. Another take-home message is unstructured sparsity can actually be very friendly implemented on CPUs if you do not care about the GPU. And if you look at the recent MLPerf benchmark, CPUs are actually taking the shot back. Recently, there is a company called Neuromagic based on Cambridge. They show that by clever co-design, they could accelerate the BERT inference using unstructured sparsity on CPU by 175 times, which is almost the GPU level, and the energy cost is not even a fraction. So I encourage you to take a look at a few top recent performance on MLPerf. And so I hope I have sold what I know about to good about unstructured sparsity and kind of convince you.
Okay, yeah, thank you. That was very helpful.
Thank you.
For anyone have a question, you can unmute yourself and ask.
Yeah.
Hi. Oh, yeah. Sorry. You can go ahead. I can wait.
I was just going to say, I'm kind of curious about the training dynamics. So like if you said that they sort of dense and sparse networks sort of come to the same solution or the same level of performance, but do they sort of, is one more stable than the other, or how do their training dynamics change when you make them sparser?
Okay, so theoretically, they are the same training trajectory up to a scaling constant change. Because the training trajectory here is simplified to a linear dynamics, we use the NTK. So that's so far the best result we know in analyzing sparse network. I'm not claiming practically that's reflected everywhere. I think people here knowing NTK know what the NTK is, right? It's just a very, very much simplification. Practically, let me tell you. So practically, if you compare the training trajectory of dense and sparse networks, their trajectory are still largely different. Especially sparse network will often have trouble in the first stage of the training chaotic. So it will often need a certain good learning rate warm up and Well, if you have teacher-student guidance, that would be great. But for the large middle training part, which is traditionally believed to be convex optimization-like, actually dense and sparse network are very similar to each other. We actually have an ICML paper this year called Training Sparse Network with Any Mask Better, where we analyze the discrepancy between dense and sparse networks, the gradient flow. And we show that by aligning the dense networks gradient flow with the sparse gradient flows statistics, it actually directly helps sparse network training out of the box. So I think still there is a hope we could borrow something from the dense training trajectory and modify sparse training trajectory, like doing some projection also.
Okay, thanks.
Thank you.
Hi, thanks for the great talks. I just have maybe two questions. Like first, I want to follow up on Matt's question. So I understand that there are some like special architecture or compilers that can help like accelerate like non-structured sparse networks. So I just to get a sense that I wonder like on a standard like maybe GPU, how much speed up can you get? Or like how many times like of memory that you can reduce?
Memory-wise, depending on your storage. If you only look at weight matrices, you store them in sparse matrix, then the element reduce is what you save, right? And in fact, we are indeed using non-unstructured sparsity to directly reduce the peak memory usage. That's relatively direct to me.
Mm-hmm.
For the acceleration, that's a tricky question. My personal experience, which maybe outdated, is unstructured sparsity on GPU lower than 50% means nothing. No acceleration on GPU without a clever implementation. 70% to 90%, it become observable in acceleration. But I would probably say 0.3 times, 0.5 times faster in practice. Nothing much than that. I would definitely not believe 2 times faster even I go 90% unstructured sparsity. And that is often because when unstructured sparsity was high enough, many of the data trunks are already fully sparse by nature because most are already sparse. So each trunk, many of them can already be skipped group by group. That's how structured sparsity saves time, right? So unstructured sparsity, when the sparsity level high to an extent, there already contains a lot of structured sparsity. That is why you can still accelerate it somehow, but still not too much. I think unstructured sparsity is not bound for CPU, not bound for GPU. I would buy unstructured sparsity much more for FPGA and the CPU.
Mm-hmm. I see. Thanks for the information. Yeah, I guess my second question would be so you mentioned like you use the wider ResNet to train on ImageNet, and by like reducing the parameter, you can get a similar accuracy as the wide ResNet. So I just wonder like how like what is the exact sparsity, like by how many did you reduce?
Sorry, I forgot to mention that 50 to 70% on ImageNet. Highest we can achieve the 70% to 72.5%.
Okay, so you can like reduce 72% of the parameters.
Yeah, nearly 3 out of 4 can be 0.
Okay, I see. Then like so because I think you mentioned that you made it 4 times wider. So yeah. I think that's so the two like
so the use a parameter number roughly comparable to the original ResNet 50. You are correct.
Okay, I see.
Our performance much wide ResNet, not ResNet.
I see. Yeah, that makes sense. So basically, you can get with a similar parameter count, you can get higher accuracy than the ResNet 50.
Yeah,
I see.
The most intriguing part here to me is optimizing a sparse large linear algebra is different from very different from a small dense linear algebra.
Yeah, I see. Thanks. Just one more quick question. So, what's the reduced parameter count? The reduced wide ResNet. The inference time would be slower than the original ResNet 50, right?
Well, it should be comparable with the wider ResNet. Should definitely slower than ResNet.
Mm-hmm. Okay, that makes sense. Thank you.
Thank you.
Just to follow up on that last question real quick, is there any intuition about why a sparse subnetwork of a dense network like ResNet 110 performs just as well as ResNet 50, or performs even better than ResNet 50, even though they both have the same parameter or similar parameter count?
Well, I think the sparse. Well, I think that this network, the network itself, get a benefit from overparameterization, right? So the dense network always, the bigger, deeper network always outperforms the shallow, smaller ones. And then the second question: why the sparse counterpart could why the sparse subnetwork could perform their dense counterpart? I tend to think this to be our architecture selection problem. Think of this way. How to say? So even if let's talk for. It's simple to think from the depth. Even I use I can choose a depth. I can choose a 10-layer dense network, a 20-layer sparse network. But intuition will tell us 20 layers should be more economic in growing expressiveness. So going deeper is worth it for me. And then going wide. Remember that here we are removing the weight, not removing the activation. Removing activation will be a total different story. I don't have a paper I can draw, but just think of a fully connected layer, input and output neuron. You could reduce many of those weight connections, but still it's very possible that input and output neuron, each neuron is still used and activated by part of data. You are still effectively using a large neuron width. You are just using smaller number of weights. You are using a sparser computational graph. So for one thing following up on that insight is actually we have another paper submitted showing that we could analytically construct a random sparse network by following the philosophy of Ramanujan graph, which is expanded graph, sparse but highly connected. We use a Ramanujan guided design philosophy. We could directly design a sparse network from scratch and perform comparably with these dense parameterized ones. So I think the key point to understand here is sparse weight is different from sparse activation. Sparse weight reduces parameter, but it does not reduce the activation you could use to construct the path from the input output, which is the true source of your computing or true source of the capacity. So that's why you probably see this discrepancy.
Okay, yeah, that's very interesting. So do you expect the same results to not hold in the case of sparse activations instead of sparse weights?
Sparse activation, I would say definitely will not hold, because sparse activation is equivalently reducing the network by half. It's
right.
Reducing activation is harder than reducing weight, right? Because if our activation, think this way, if one activation is reduced, then every weight connected to that activation is simultaneously eliminated. So it's actually harder.
Right. Okay, thank you. Yeah.
Thank you.
Okay, so I think given the limitation of time, let's thank Professor Atlas once again for this great talk.
Thank you for having me.
Bye.
All right, bye. Thank you.